Welcome to the seminar on model-based design of an SUV anti-rollover control system, sponsored by Mechanical Simulation Corporation and the MathWorks. I'm Tom Gillespie of the Mechanical Simulation Corporation. In a few minutes, we'll be joined by my colleague, Vinod Cherian of the MathWorks. Together, we'd like to talk to you about rollover, one of the more important vehicle dynamics issues facing the automotive safety community today. First, I'll give you some background on the rollover problem. Then I'll introduce one of the tools that has been so helpful in solving this problem, the CarSim Vehicle Dynamics Simulation software. CarSim will be used as a virtual vehicle model for development of solutions to the rollover problem. The solution takes the form of an anti-rollover controller. This is where Vinod will step in and talk about design of the controller using tools available in Simulink and methods to optimize the design of the controller. After Vinod finishes his summary and conclusions, we will both be available to answer any of your questions. Rollover can occur just about anywhere, in many cases without any interaction with other vehicles. On the open road, just a moment of distraction, allowing wheels to leave the road at high speed, can precipitate loss of control, often leading to rollovers as seen here. These are known as single vehicle accidents. The interest in this type of an accident arises from the fact that it is so common and involves only a driver and a vehicle. Thus, we can potentially prevent many of these accidents if we can improve the vehicle's dynamic behavior to make it more controllable. Rollover is a high-risk accident type. Even though they are only 2% of all accidents, they account for approximately 25% of highway fatalities in the United States every year. Consequently, there's a lot of interest on the part of the automotive industry and government to find ways to reduce the risk to the driving public. In the United States, NHTSA, our National Highway Traffic Safety Administration, began trying to regulate rollover performance as far back as 1973. By devising a rollover standard for new vehicles. It gives you a clue as to how difficult the problem has been when you realize it took them until 2003 to devise a rollover test acceptable to all the stakeholders in the automotive and safety communities. The test they adopted is known as the fishhook. It is used in evaluating performance for the STAR safety ratings assigned to new passenger cars. Continuing development of the test method led to the Sign with Dwell test adopted in 2006 for the Federal Motor Vehicle Safety Standard 126. FMVSS 126 requires electronic stability controls on all light vehicles by the 2011 model year and specifies dynamic performance requirements for the ESC. Since it's a Federal Motor Vehicle Safety Standard, all new vehicles will have to meet the requirements of the standard in order to be sold in the United States. This same requirement has been adopted in Europe under UNECE Regulation 13. To give you a feel for rollover testing, we'll take a few minutes to look at the fishhook. Rollover test procedures generally begin with a steering calibration. The purpose is to adjust the procedure for the steering gain of the test vehicle, since steering gain varies among vehicles. The calibration measures a reference steering wheel angle, which is the angle that produces 0.3 Gs of lateral acceleration at 80 km per hour. The test steering wheel angle is then set at 6.5 times this value. The rollover test procedure involves driving the vehicle at a prescribed speed on a skid pad and applying the steering input shown in this graph at lower left. The tests cover a range of speed and load conditions. This is a very aggressive test, requiring steering at high rates to exact angles, which are precisely timed to the vehicle roll response. The test begins with a steer in one direction to the test steering wheel angle at the rate of 720 degrees per second. Then, just as the vehicle rolls to its maximum angle indicated by the drop in roll rate to less than 1.5 degrees per second, the steering is ramped in the opposite direction to the same angle, again at the rate of 720 degrees per second. The vehicle fails a test if there is a liftoff of the two inside wheels. To be able to accomplish this steering input in actual testing, an automated steering actuator is required. The additional requirements for vehicles, instrumentation, and test facilities makes simulation an attractive alternative to experimental testing of the fishhook. I can show you an example of the fishhook test in this animation of 3 vehicles made with CarSim. The front vehicle is stable throughout the test. The second one becomes unstable, sliding sideways, and attempts to roll over, but is prevented by the presence of the outriggers. The rear vehicle goes roll unstable at the outset, but is allowed to roll over. I can show you this again from a different angle using the CarSim animator, pan, and zoom features. The other rollover test is the FMVSS 126 procedure for ESC testing shown here. The procedure is quite similar to that of the fishhook, differing by the use of a sign with dwell steering input and testing at increments of steer angle rather than increments of speed. Overall, it's a complicated test procedure requiring demonstration of adequate steering response, seen here in the requirement to achieve lateral movement of 1.83 meters, and then stable behavior indicated by good control of yaw rate at specified time intervals following the completion of the steer. As with any federal motor vehicle safety standard, compliance with this standard must be certified in order to sell the vehicle. This slide shows an animation of the FMVSS 126 test on a sedan without ESC. The animation has been edited to show only selected portions of the test, starting with a steering calibration, then testing at increments of steer angle until failure occurs due to uncontrolled yaw rate. Designing and developing vehicles that meet these requirements presents challenges. You might wonder, how can one design a controller to prevent rollover? Rollover occurs when excessive lateral acceleration combines with a gravitational acceleration into a resultant shown here in red. If the lateral acceleration grows large enough that the resultant falls outside of the wheel track, rollover begins. Lateral acceleration arises from a sideways drift of the vehicle. That is, the angle between the direction it's pointed and the direction it's traveling. If we let this angle build up, so does the lateral acceleration. Thus, by rotating the vehicle into its direction of travel, the lateral acceleration can be decreased to prevent rollover. On modern cars, we have a way to do this. The control of individual brakes that are part of the anti-lock braking and traction control system allows us to brake wheels on just one side of the vehicle to rotate it into its direction of travel. Though a simplified explanation, this is the function of an anti-rollover controller, such as an electronic stability control. Meeting these requirements challenges the OEM and Tier 1 suppliers in several ways, specifically designing the controller and testing to verify its performance. Controller design involves several challenges. One is to devise an algorithm to use whatever information can be measured or estimated regarding the vehicle state to achieve stability. Difficulty in tuning the controller parameters using analytical methods adds to the effort. And finally, maintaining compatibility with other systems like the ABS, traction control, or electronic stability control are also required. Testing presents other barriers due to its expense, because of the need for vehicles, test facilities, test equipment, engineering time. And experimental testing always presents difficulties in obtaining repeatable results. And third, tuning the solution needs to be repeated for every vehicle variation or configuration. Even then, it can be impossible to prove safety-critical systems over all possible driving scenarios. Simulation provides the means to develop and prove out a design. CarSim can provide the vehicle dynamics component of the solution to this problem. It's a time-based dynamic simulation program that is proven and validated over more than a decade. It's used by major OEMs like GM and Toyota and by the major Tier 1 suppliers. It's real-time, so you have fast solutions. And it's an all-in-one turnkey program because it comes with multiple examples, so you can immediately make runs or modify data, has a built-in animator that allows you to look at the test results immediately, and it has a built-in plotter that gives you instant quantitative results. CarSim comes with vehicle data sets for a dozen vehicles, from A-Class through F-Class, sedans, sports cars, vans, SUVs, and pickups. As we'll see, the models can be modified with Simulink or C-Code. CarSim includes dozens of test procedures, including the fishhook and FMVSS 126. An events feature allows users to monitor variables during the progress of the procedure and make changes when desired. For example, events allows a tire data set to be replaced in the course of a run to simulate a tire blowout, or to construct complex maneuvers such as the FMVSS 126 sequence. CarSim includes numerous test sites to choose from, such as road courses, skid pads, hills, curves, circles, and varying friction and wind conditions. Once the user has selected the vehicle, procedure, and test site, a click of the Run button causes the execution of a solution faster than real time. And upon completion of the run, the user can immediately animate the results to make sure the test proceeded as planned, and then click on the plotter to examine the results in detail. In terms of the vehicle model itself, CarSim is a core model with high-fidelity representation of the major automotive systems. The basic systems are the body, suspensions, engine and powertrain, steering, brake systems, and tires. CarSim also has trailer options. In the design of CarSim, it was recognized that experts working with each of these systems will potentially want to add detail to the model of their system or implement a corporate model. So CarSim has been configured to easily accommodate additions or substitutions for each of the systems in the model. For example, steering system engineers can enhance or replace the CarSim steering model with their own formulation in Simulink or C-Code, yet still use the same core vehicle model as their colleagues in other departments. If appropriate, they can even share their special steering model with others by exchanging parameter files. If it's necessary to share files with others outside of the company, for example, a supplier, portions or all of the files can be encrypted. This close working relationship with Simulink is reflected in the easy and convenient co-simulation environment created for CarSim and Simulink. CarSim is set up so that the main screen has provision to interconnect with Simulink as seen here in the left-hand image. Simulink is routinely used with CarSim when a controller needs to be modeled, in which case CarSim simply becomes an S function within Simulink. Then the simulation itself can be controlled either from Simulink or from CarSim. Once the controller has been designed and reproduced in hardware, this same environment can be used for testing the hardware with exactly the same vehicle model in CarSim real time. CarSim, installed on a host Windows machine, provides the same familiar interface with animator and plotter functions. The real-time solver is installed on a target computer with a real-time operating system to talk with the controller hardware. With this easy and convenient interconnection to hardware, CarSim is being used extensively for HIL testing throughout the world, including serving as the vehicle dynamics model on over 100 driving simulators. In review, CarSim is a natural partner for co-simulation with Simulink. It is a proven and validated vehicle dynamics solution, providing the selection of vehicle models, test maneuvers, and animator and plotter functions necessary for control development. Best of all, it's easily integrated with Simulink, presenting the user with a familiar environment for creating the controller functioning as a subsystem in a CarSim vehicle dynamics model. I'm now going to turn the presentation over to Vinod for discussion of the controller. The example we will use today is a standard vehicle model from CarSim for a midsize SUV, and we'll use the NHTSA fishhook test from CarSim as the benchmark for testing the controller's effectiveness.